Okay, well, we begin today's lecture with the beginning of Chapter 10. Chapter 10 is also about chemical bonding, second chapter on chemical bonding, because we didn't go over everything relevant about bonding in the first chapter. This is some different stuff, including things like the molecular geometry, that is, what shapes do molecules actually have. You may have noticed that we never actually got to that in the last chapter. And also valence bond theory, which adds some new aspects to our view of bonding, and maybe molecular orbitals. We're not really probably going to say much about that, but that is in this chapter. So beginning with molecular shapes, or working up to how to find the molecular shapes, we start with the VSEPR theory. The shapes of molecules are very important to know, or to be able to figure out anyway. And that's because many properties of molecules, like polarity, state, that is, are they a solid or a liquid or a gas at room temperature, and for biomolecules like proteins and enzymes, function is also closely related to structure and shape. If you take a protein and change its shape, you will change its function, and it may not function at all, or it may do something you don't want it to. So actually being able to determine the shape of a molecule is a pretty important thing. For things like proteins, scientists generally now use computers to determine the shapes of big complicated molecules like that. But the software that they use on those computers is programmed using the same kind of basic stuff that we're learning here, with a lot of other higher level information that comes later. So starting with VSEPR, VSEPR is one of the ways to determine the shape of a molecule. And VSEPR stands for valence shell electron pair repulsion theory, which is a bit of a mouthful, and that's why they call it VSEPR. Sometimes called VSEPR, but it doesn't really spell VSEPR. It spells VSEPR. So we'll call it VSEPR. What it says is that electron pairs repel each other. Because, of course, they have similar charge. They're negative charged. So, of course, one negative charge is going to repel another. As a consequence of that, electron pairs will get as far apart from each other as possible in 3 dimensions. And when those electrons are valence electrons of the central atom of a molecule, it's especially significant. Because when valence electrons on the central atom of a molecule do this, they determine the shape of the molecule. Because the outer atoms are connected to the central atom through bonds, And so atoms, the outer atoms can only occur where bonds are able to form. Okay, so you're only going to find outer atoms around the central atom in those locations where bonds are able to form on the central atom. And the locations where bonds are able to form will be where the electrons are. So if the number of valence electrons around a central atom basically dictates that they have to get as far apart from each other as possible, and that results in a certain area not having any valence electrons in it, then that's a certain area where there can't be a bond. On the other hand, if that policy dictates that a pair of valence electrons will be in a certain area, then that's an area where there could be a bond. And all of this, again, affects the shape of the molecule. Okay, so this is all about trying to determine the overall shape of the molecule. For simple molecules, and by that I mean one central atom, like most of the ones we've been looking at so far. Then you really only have to check the central atom to determine the shape of the molecule. And so the things that would affect the shape of the molecule for one of these simple molecules, that is the kind where you've got one central atom surrounded by the other atoms, would be the number of electron pairs on the central atom, particularly that is valence electrons, and the relative number of lone pairs versus bonding pairs. For right now, we're going to deal with the simplest cases. And that is simply when all of the electron groups on the central atom are bonding. Or that's another way of saying no lone pairs on the central atom. And the result of this is the 5 basic shapes. There are actually more than that, but the 5 basic shapes are all we really need to be concerned about in this class. Because when you get beyond that, the five basic shapes, they get pretty complicated, and you get large, complicated molecules, and there aren't really that many molecules of those types anyway. So we're going to look at anywhere from 2 to 6 electron groups on the central atom. Okay, so for one, we'll start with one actually. One electron group on the central atom is a very simple case. Because, well, there's no central atom, first of all. There are only 2 atoms total. In a case like this. And the important thing, though, is that 2 lines or 2 points define a straight line. So if you've only got 2 atoms in the molecule in shape has to be linear. There's really no other way about it. So a case like this might be hydrogen. That's the simplest one. The Lewis structure for hydrogen can be written like this, with H dot dot H or H line H. And obviously the only way you could arrange those 2 atoms would be in a straight line. No matter which way you orient them, they're going to be a straight line. HCl is also an example. Whoops, sorry. Okay, so you can have either of those as the Lewis structure. Obviously, it has to be linear. All right, so let's get a little more interesting. 2 electron groups on the central atom. Okay, this will also be linear, as long as those 2 electron groups are all there are, all you have on the central atom. There aren't a whole lot of examples of this, but a couple of them would be, for one thing, beryllium chloride, BeCl2. And that'll have a chlorine, and then beryllium, and then another chlorine, with lots of lone pairs on the chlorines, but not on the beryllium. So you notice there are only 2 electron groups on the beryllium, no lone pairs on the beryllium or anything. And so the way that these electron groups can get as far apart from each other as possible is to be directly opposite one another, just like they are in the way I drew the Lewis structure. You could also draw the Lewis structure like that. And again, you can see clearly that the electrons are as far apart from each other as possible when they are directly 180 degrees apart from each other. We need to study the geometry of these molecules, though, because the Lewis structure, and I'm going to point this out again and again just to keep reminding you, the Lewis structure does not necessarily show you what the molecule really looks like in real life or in 3 dimensions. The Lewis structure just shows you what is bonded to what and how the bonds are set up. But when it shows you what the molecule really looks like it does in this case, it's sheer coincidence. It doesn't, and in fact, there are other ways that you could draw this Lewis structure for BeCl2. It would be just as correct to write it as this. This Lewis structure is just as correct as either of these two. And that makes it look like the molecule is bent. But it's not. It's actually 180 degrees linear. And that's because, and we can tell that just because that is the way that these electron groups, the two pairs of electrons on the beryllium, can get as far apart as from each other as possible. If it were like this, bent at a 90-degree angle, then obviously the two electron groups would only be half as far apart. So it's definitely going to be linear. So 180 degrees is as far apart as they can get. Another example is CO2. When we do the Lewis structure for CO2, we end up with this. Or this. And you notice that there are two groups of electrons around the central atom, and they will get as far apart from each other as possible. So this is a linear molecule also. And the bond angle is 180 degrees. It's important to note at this point that we count the double bonds as one electron group, just like we do with single bonds, because in reality, double bonds only take up a little bit more space on the atom than single bonds do. It's not twice as much space. It's nowhere near twice as much. And so when we say one electron group, that could be a single bond. It could be a double bond. That counts as one group of electrons. It could be a triple bond, because a triple bond only takes up a little bit more room than a double bond. Or it could be a lone pair. Each of these counts as one group or one region of occupation when it comes to electrons. So you have to keep that in mind when you're doing Lewis structures and then trying to go on beyond that and figure out what the shape of the molecule is. That a double bond, that counts as one group or one region. The triple bond, that's one group or one region, and so on. Okay, so what if you have 3 electron groups? Again, on the central atom. The molecular geometry in this case and that's another word for molecular shape. In this case, it's trigonal planar. Or if you prefer the Mercedes emblem. Basically, the molecule looks like that. And the standard bond angle that you find in an ideal case would be 120 degrees. Because when you have 3 things and you want to get them, well, basically they're all attached to one central point, and you want to get them otherwise as far apart from each other as possible, the way to do it is have them all in the same plane 120 degrees apart. There is no other way that you can get them any further apart than that. As the name implies, planar means flat, and trigonal means 3-sided. An example of that would be aluminum chloride. AlCl3. When you do a Lewis structure, you end up with one of these. And it looks, the way we usually draw the Lewis structure, it looks more like it's T-shaped, with angles of 90 degrees, but it's not. You could also, if you kind of know ahead of time what's coming and you think ahead, you could draw the Lewis structure in a way that it does reflect the actual geometry. Because again, Lewis structures are quite flexible in that it doesn't really matter. The exact arrangement of the atoms doesn't usually matter. What really matters is what is bonded to what and how. So as long as you have each chlorine attached to the central aluminum with a single bond, it doesn't really matter how you group the chlorines or how you arrange them around the aluminum. So in this case, this Lewis structure really does reflect the actual structure of the molecule, whereas these two don't. And there are any number of other different ways that you could draw this Lewis structure that would be equally correct, which also would not reflect the actual geometry. Okay, so three electron groups around a central atom will be farthest apart when they're separated by 120 degrees. Okay, so they're equidistant around the central atom in the same plane. And so we have 120 degree angles. And the VSEPR structure would be the one where you draw the molecule that reflects the actual arrangement. You don't have to write the bond angles in for a VSEPR structure. And also notice that for VSEPR structures, we usually leave out lone pairs on outer atoms. That's for the VSEPR, not for the Lewis structure. For the Lewis structure, you have to include all of the lone pairs. Another example of this case would be formaldehyde. Or CH2O. In this, the carbon is the central atom. And the oxygen and two hydrogens are attached like so. You end up having to use a double bond for the oxygen in order to give carbon an octet. You can also draw it like that. And the geometry is the same as aluminum chloride, more or less. Because you've got three electron groups around the central atom. The single bonds account for one group each, and the double bond counts as one group. So 1, 2, 3. And so they will get as far apart from each other as possible in 3 dimensions. and you end up with something that looks kind of like that. It's okay, maybe not quite as lopsided as that, and maybe the angles are a little closer to what they should be. My artistic ability is kind of inadequate. The angle between the oxygen and the hydrogens are actually 121.9, a little bigger than you'd expect for a trigonal planar structure, because the, like I said, the double bond doesn't take up very much more space than a single bond, but it does take up a little more. And that's enough to push the hydrogens a little bit closer together compared to what you would normally expect. And so their angle is only 116.2. You don't have to know those angles. Just know the effect that the double bonded oxygen has on them by pushing the hydrogens a little closer together. That's the important thing, not the exact number of the angle that it ends up with. Now let's see, 4 electron groups. This is where things get fun. Because this is where molecules actually become three-dimensional, when you reach 4 electron groups on the central atom. So these molecules are no longer flat. There is a table on page 408 in the textbook that you can look at. Oh, yes. Just to make sure that I'm looking at the right one. Okay. Yeah, there is a table on page 408, and we haven't gotten to everything in this table yet. But essentially, the top line in each section, that's what we're talking about right now. So we went over what happens if there are 2 electron groups and both of those electron groups are involved in bonding. Well, you have a linear geometry like, oh, look what the example is, CO2. And if you have 3 electron groups and all 3 of them are involved in bonding, there are no lone pairs on the central atom, then you have trigonal planar. That's what we just did. BF3 has the same geometry as AlCl3. What we're on now is 440. That is 4 electron groups around the central atom, all 4 of them involved in bonding, no lone pairs on the central atom. And here's our geometry, which we'll mention in a moment. Here's a Lewis structure for a molecule of this type. And here's what they really look like in 3 dimensions. And so these 3-dimensional drawings down the right-hand side are better than anything I could do. So you might want to look at those while we're going over this. Also, molecular models can help. And so I have some of those that I'll pull out from time to time. And so the shape of this molecule would be tetrahedral. Or the molecule itself would be a tetrahedron. And what this is like a pyramid with a 3-sided base is basically a tetrahedron. So it's basically a 3-sided pyramid. The example used but in the book and by me is going to be CH4 or methane. Lewis structure would be something like this, or like that, which makes it look like the molecule is shaped kind of like a plus sign with 90-degree angles and flat, but it's not. These angles here would be 90 degrees, but it's possible to get them further apart. And by forming a tetrahedron, the electron groups around the central atom can actually get 109.5 degrees apart. That's, that's quite a bit further apart than 90 degrees. But this requires it to become three-dimensional. So what you end up with is the shape like I showed you in the book. Another way you can think of a tetrahedron, you can make one with your hand, actually. If you take one hand and your other hand and put them together like this, with this right here being the carbon, and the fingernails on your index fingers and thumbs will be the hydrogens. You can get a rough idea of what a tetrahedron looks like that way. So that's one way of looking at a tetrahedron. Also, molecular models would not hurt. This is a tetrahedron right here. As you can see, if you lay it flat on a surface, it stands up a little, stands up a little bit. This isn't working so well. Okay, how about this? You can see that it stands up a little bit from the surface, and it is, in fact, three-dimensional. If all of the outer atoms are the same, like they are in CH4, then all of the positions on the tetrahedron are equivalent to each other, and you can flip it over and around in every which way, and you won't be able to tell the difference. In drawing a tetrahedron, it can be a little challenging to draw it on a flat two-dimensional surface like paper, but I find usually if you hold the molecule something like this, you'll notice that you have one bond that's sort of perpendicular to your face and another bond that's perpendicular to your face. So we usually draw those as straight lines in diagrams. And at the same time, you have another bond that's coming sort of downward and towards you. We usually draw those as wedges with the broad end towards you, like that. And then there's another bond that's going down and away from you, this one. And we draw those as a dotted wedge with the narrow point pointing away from you. So that is about my best representation of this molecule here. And it's good enough that you can sort of tell what it's supposed to be. And that's about the best we can expect from a person drawing something on a two-dimensional surface like paper, unless you're a really good artist, which I am not. Also, there are some diagrams in the books. The book helps you visualize these shapes by saying, think about what would happen if you tied 4 balloons together. The 4 balloons sort of representing the lobes of orbitals. And if you had 4 balloons tied together, they would adopt this kind of shape here, which is a tetrahedron. If you connect the outermost points, furthest away from the center for each of these 4 balloons, you get a tetrahedron, which is a 3-sided pyramid. And then here's the Lewis structure, and here's the representation of the 3D structure. Okay, so that's tetrahedron. Or tetrahedral. All right, so suppose you have 5 electron groups. Oh, we're over 30 minutes, so next will be 5 electron groups.